Hello, everyone. My name is Bettina Burke, and I am part of the ME62 Senior Design Team, which is focusing on the thermal fluid study of heat transfer and pressure drop of 3D printable open cell foams. My partner is Christian Bollinger, and my sponsor is Dr. Chu. For our problem statement, we are utilizing previously published and newly generated open cell simulation results to analyze, print, and test upon 3D cells that each have different geometric and material properties.
We were able to successfully print cells with binder angles ranging from 30 to 60 degrees. This was accomplished using three machines: the Stratasys F370, which printed with ABS, the Connex 350, which printed with digital ABS, and the Formlabs Form 2, which printed with clear resin. After successfully printing these cells, we decided to explore the feasibility of printing cells with smaller binder angles. We were concerned that the cells would be damaged when handling, so we simulated the force of handling each cell to determine if they would break. A force, represented by the purple vectors, was applied to one branching face while the opposite face was fixed, represented by green bolts. We tested applied forces of 1, 10, 15, 50, and 100 newtons, and used ABS material properties in the simulation. Cell 6, with the thinnest supports resulting from the smallest binder angle of 5 degrees, failed after only 15 newtons of force was applied. The ultimate yield strength of the material is 48.3 megapascals, while the maximum von Mises stress present is 75.1 megapascals. Cell 7, with a binder angle of 10 degrees, fails after 100 newtons of force are applied with a maximum von Mises stress present of 53.88 megapascals. Cell 8, Cell 9, Cell 1, with binder angles of 15, 25, and 30 degrees respectively, do not fail with 100 newtons of force applied. Cell 1 was used as a control as it was printed and handled successfully. This graph explicitly displays the relationship between binder angle and maximum von Mises stress present with 100 newtons of applied force. Maximum von Mises stress present decreases with increasing binder angle. The orange line represents the yield of the material. To validate the results of the simulation, compression testing was performed on samples with binder angles of 5, 10, 25, and 30 degrees using ABS. A second trial was performed using digital ABS and cells with binder angles of 10, 20, 25, and 30 degrees. In trial 1, each cell failed with a stress much smaller than the ultimate yield strength of ABS, 48.3 megapascals. Additionally, most cells failed with less than 100 newtons of applied force. This was attributed to layers formed by the 3D printing process, which caused the faces to fracture between these layers as the applied force increased. It is also worth noting that two 5-degree cells were printed, but one sample had multiple breaks at the supports due to handling, so it could not be tested. Trial 2 was conducted using cells printed with digital ABS. These cells had smoother surfaces and stronger bonds between layers of material. Failure occurred due to fractures forming between layers similar to the failures in Trial 1. These failures occurred at higher stresses and loads than Trial 1. Cell 7 was tested in a cube formation to observe if the cause of failure would be the same. Failure was caused by support deformation. An additional simulation was performed with this load condition on Cell 7. 167.3 newtons, the load at initial break, was applied. The resulting maximum von Mises stress present was 46.88 megapascals, close to the ultimate yield strength of 48.3 megapascals, and was concentrated in the supports.
We next conducted CFD fluid flow tests in COMSOL to analyze the pressure drop across open cell foams. We created the foams in SolidWorks, removing the branches that face the inlet outlet ends for airflow of the boundary box. This way, the airflow is not initially obstructed. The first trial utilized the 5-degree cell. These cells each have a porosity of 0.96. The same plate formation 3x3 was used in all trials. For the setup of the boundary box, it was set to be 3 times the characteristic length of the foam with a symmetric condition on the longer faces. The shorter faces served as the inlet and outlet ends for airflow. A tetrahedral mesh was used in the simulation. There was a fine mesh with general physics properties for the foam and a normal mesh with fluid dynamic properties for the box. The foam was set to be resin, while the box was set to be air at room temperature. For the first trial, we wanted to analyze the impact of porosity on pressure drop. When utilizing the 5-degree cell plate, a maximum pressure drop of 57.3 pascals resulted. The velocity magnitude contour is also shown. For the next trial, we wanted to decrease porosity from 0.96 to 0.7. This was done by utilizing the 30-degree cell. The airflow speed was kept the same. When running this foam in COMSOL, the maximum pressure drop resulted in 72.8 pascal value. As one can see, porosity is inversely proportional to pressure drop. Next, we wanted to see how airflow speed impacted pressure drop. So we doubled the airflow speed from 5 meters per second to 10 meters per second, still utilizing the 30-degree cell plate. The pressure drop resulted in a value of 292.3 pascals. From this simulation, one can see that airflow speed is directly proportional to pressure drop. The last goal we wanted to maintain and achieve was a final proof of concept print. We created the 3x3 plate with the 30-degree cell using the Stratasys F170 printer that printed the plate in ABS. Thank you.